Today we discuss section 27, that is prime and maximal ideals. In this section, first we can see a few examples. As we all know, if Z6 is a ring, and if you consider Z6 is ring under addition modulo 6 and multiplication modulo 6, and if we consider an ideal, that is ideal 0, 3, obviously is an additive group, and which has the property that if you multiply any element r into 0 and r into 3, r into 0 is always 0 and r into 3 is always a multiple of 3. Okay, so that is 1 into 3, 2 into 3, etc. are all multiple of 3. So if you multiply any r into 3, then this r can be one of these elements. 1, 2, 3, 0. Obviously 0 is also there. 4, 5. If you choose any of these 6 elements, then multiply it with 3, then that will either 0 or 3 itself. Okay, so we can say that this is an element of singleton set 0, 3 also as well. So this satisfies the condition of ideal. Okay, so this is an ideal. I call it as n. Then obviously this ideal generate or ideal, we can use this ideal to define factoring is at 6 over n. Okay, so obviously this contains 3 elements because number of distinct left coset is 3 because it contains 2 elements. Z6 contains 6 elements. Then 6 by 2, there are 3 distinct left cosets are there. These are this one plus n, 2 plus n. Obviously this is isomorphic to Z3. You can easily verify that this is Z3. So Z6 over n is isomorphic to Z3, but this is a field. Okay, even though this Z6 is not a field. It's not a field. Even though this is not even an integral domain because there are 0 devices are there. So if this ring Z6 is not an integral domain, but the quotient ring will have the property of the field. So this is also possible. So this kind of examples are discussed in the first part of this section 27. Now you can see two interesting definitions. One is improper ideal. Improper ideal is for every ring R. R is always a subgroup of R itself. Therefore, this R has the property of the ideal. Then this R is called improper ideal. Improper ideal. Similarly, if you consider singleton set 0, this is always a additive subgroup of R. And if you multiply any element of this set with any element of R, then that will give 0 itself. So that is also an ideal. So this ideal is also called trivial ideal. Like trivial subgroup and improper subgroup, this is trivial ideal. So there are two interesting ideals are there for every arbitrary ring. So this is trivial ideal and this is improper ideal. So any ideal other than these two, okay, any ideal other than these two ideals, improper and trivial ideal, are called this is not equal to 0, this is not equal to R. This ideal is called proper ideal, which is non-trivial. Proper ideal, and this also non-trivial. So non-trivial proper ideal. Okay, non-trivial proper ideal is ideal which is not equal to R and which is not equal to 0. So this kind of ideals are there. You can see the next theorem, theorem 27.5. In this theorem it says that if R is a ring with unity and n is an ideal, okay, of R, if any, so we have a ring R and there is an ideal n, if this n contains at least one unit, okay, so if U is a unit, then obviously unit means U has multiplicative inverse in R. So U inverse is there in R, somewhere in R. So we know that if you choose an element of n and an element U inverse of R, then if you multiply these two, this is always an element of n itself. Okay, so this product U inverse is always a member of n itself. So whenever an ideal contain a unit, okay, say a unit U, then we can say that 1 is always a member of n. Okay, so 1 is also always a member of n. If 1 is always a member of n, then if you choose any r belongs to r, then 1 into r is always a member of n itself. So for every r belongs to r can be written as 1 into r, that is also a member of n, because the definition of the ideal. If you multiply any element of n and any element of r, the product is in n. So which shows that every element of r is a member of n. What is the meaning of this? R is contained in n. Since this n is an ideal, n is always contained in r, and these two inclusion together says that n equal to r. So this 27.5 says that if n is a ring with n is an ideal with unit, then n is same as r itself. Okay, so this is, as a corollary, we can easily prove that this field has no non-trivial proper ideal. Okay, because if f is a field and there is an n, okay, which is not equal to 0, this is an ideal of f, then you can easily prove that n is equal to f, because this n has at least one non-zero element belongs to n. We know that belongs to n, which is contained in f itself. Then u is a non-zero element of f, then we can say that u is a unit. U is a unit in n. Whenever an ideal contains a unit, then n is same as the whole ring f itself. So we can say that any ideal which is not equal to singleton set 0, then that n is f itself. So f has only two ideals. So this is the corollary 27.6, a field containing no proper non-trivial ideals. Now we can define maximal ideal. This is the definition of maximal ideal. A proper ideal is said to be maximal if there does not exist any proper ideal which properly contains m. Okay, so this is the definition of maximal ideal. That means m is maximal if and only if the only ideal which properly contains n. Okay, if there is an ideal n, this should imply n equal to r. This is the only possibility. See? This is the largest ideal. You can say that there is no proper ideal which properly contains. Okay? If there is any ideal which properly contains this m, then that ideal is nothing but r. Okay, so the other way you can say that whenever there is an ideal n contained in r, this is not possible. Okay, this kind of ideals will not be there for a maximal ideal. If m is maximal, there does not exist such ideal n. Okay, that is, whenever we have an ideal n in between m and r, and if m is maximal, you can easily conclude two things. Either this m is same as n, or n is same as r. Okay, there are no other possibilities. Okay, if m is maximal, then these are the only two possibilities. Okay, so this is the definition of maximal ideal. Then immediately we can prove theorem 27.9. If m is a maximal ideal, if and only if r by m is a field. Okay, so in order to prove r by m is a field, we need to prove that we start with a ring commutative ring with unity. So this r by m is also a commutative ring with unity. Then in order to prove r by m as a field, we will prove that every non-zero element, suppose this is non-zero element of r by m. Obviously non-zero zero in r by m is nothing but 0 plus m. Okay, if this is not equal to 0 plus m, that is the meaning of this is non-zero, then this is not equal. Then we will prove that this a plus m has multiplicative inverse. Okay, so before we prove this theorem, we just observe that if we have a commutative ring with unity, and if we choose any a belongs to r, then you can define a set of all multiples of a. Okay, consider set of all AR. Since this is commutative ring, then AR is same. Since this R is commutative, then AR is same as RA. So you need not worry about the other product. So you consider all these elements and you put it as I, then this I is an ideal. Okay, you can easily prove that this is a I under addition is a group, and if you multiply any R1 with any element of this, then you can say that this is same as R1R. Okay, that is contained in I itself. So if you multiply it with the right side, that will same happen because this is a commutative ring. So if you start with any element of R, you can generate an ideal. Okay, that ideal contains only multiples of A. Okay, so this is denoted by this. This consists of the set of all multiples of R, multiples of A. So if you start with a non-zero element A plus M belongs to Rn, then this generates is an ideal. Okay, so that is set of all multiples of A plus M. That means if you choose any arbitrary element from R by M, R over M, and multiply it with A plus M. Okay, this is set of all Rm. So we define this. Obviously this is not equal to, or this is properly contains 0 plus M. Okay, because this contains at least A plus M. A plus M is not equal to 0, then this is not equal to singleton set 0. Singleton set 0 plus M. Obviously this is contained in R over M, and this is an ideal as well, because this is the ideal generated by A plus M. Instead of taking A here, then we take A plus M, an arbitrary element of this ring R over M. Okay, then you consider this. Okay, so obviously this is an ideal. We know that there is a canonical homomorphism. This is what we have explained in the textbook here. So this consists of set of all multiples of A plus M. That means R plus M into A plus M, where R plus M is a member of R over M. So that set is denoted by, instead of taking I, they denoted this symbol R over M into A plus M. Okay, you consider this set, and this is not trivial because this is not equal to 0 plus M, and it is a proper ideal because we know that this 1 plus M is not a member of this. Okay, 1 plus M will not be a member of, or will not be a member of this set R plus M, A plus M. Okay, otherwise this will be the whole ring R over M itself. Okay, so if this is the case, then or if you have a 1 plus M is a member of this set R plus M into A plus M, then we are done. So nothing to prove, because 1 plus M is a member of this, means there 1 plus M can be written as R plus M into some R1 plus M into A plus M. Okay, which shows that A plus M has multiplicative inverse. Okay, so if 1 plus M is a member of this set, then we are done. So if this 1 plus M is not a member of this, then you can say that this is not equal to R over M, and this is not equal to, and this is an ideal. Then you consider the canonical homomorphism gamma from R to R over M. Okay, so every ideal here, then gamma inverse I is an ideal of R. Okay, so if you call this is the ideal I, then gamma inverse I is an ideal of R, which properly contains 0 and properly contained in R. Because this is not equal to the whole ring R over M, then by taking inverse image we will not get the whole R. Okay, because this map is onto. So we have an ideal, and this fully contained in it. And what is the other importance of this? We know that if we choose any M belongs to M, then gamma M is nothing but M plus M, that is equal to 0 plus M. Clear? So every element of M is mapped to 0 plus M. Okay, so once you observe gamma inverse of I, then we need to consider all the pre-images of elements of I. Okay, this I always contains this element 0 plus M. So if you consider gamma inverse of I, we need to collect all the inverse images of 0. What are the inverse images of 0? Every element of m is mapped to 0 plus m. So if you find the inverse images of 0 plus m, we need to collect all the elements of m itself. So gamma inverse, not only this is contained in gamma inverse, this m is also contained in gamma inverse of I, which is properly contained in R. So which is a contradiction, because this is an ideal and we assume that m is maximal, then there is an ideal in between m and R. So this is a contradiction. Okay, that means if we start with a plus m, then 1 plus m does not belong to this is a contradiction. Hence this 1 plus m always belongs to, that's it, otherwise we will have a contradiction. Okay, so whenever 1 plus m is a member of this, then you can easily prove that this a plus m has a multiplicative inverse. So this is what we can see in the first paragraph. Now conversely, we assume that R over M is a field. Okay, then you can prove that M is a maximal ideal. So in order to prove M is a maximal ideal, we suppose an ideal in between M and R. Okay, then apply gamma. Then gamma M is trivial and gamma R is R over M. Then gamma n is in between this. We already proved that we already assumed that R over M is a field. So the only possible ideal is either this is trivial ideal or this is R over M itself. Okay, because we have already proved that a field has no proper non-trivial ideal. Okay, so what does it mean? Whenever gamma of n is equal to 0 plus m, that means every coset using elements of n is m itself. That means n is equal to m. Okay, so either if this gamma of n is equal to 0 plus m means that m is equal to n, or otherwise this is equal to r over m. That means gamma of n is equal to r over m means n contains all the cosets of r over m. Okay, that means this n is equal to r. In order to get the whole cosets, we need to collect all the ring as well. So if this happens, we can say that either m is equal to n or n is equal to r. So which shows that m is a maximal ideal. So this is the other part. R by m is a field if and only if m is a maximal ideal. Now we have a corollary. A commutative ring with unity is a field if and only if it has no proper non-trivial ideals. So the one part is very trivial. If we start with a field, a commutative ring is a field, then we already proved that it has no proper non-trivial ideals. Conversely, we need to prove all the converse only. If R is a commutative with unity, has no proper non-trivial ideals. Suppose this, then 0 is the maximal ideal. Okay, if there is no ideal means the maximal ideal of R is singleton set 0. We already proved that this is the maximal ideal. So since this is the maximal ideal, then R over 0 is a field. Okay, so but we know that R over 0 is isomorphic to R itself. We already proved that using fundamental theorem, this by identity function from R to R, the kernel will be singleton set 0. So R over singleton set 0 is isomorphic to R itself. And we know that R over 0 is field means R over 0 is isomorphic to R, implies that R is also a field. Okay, so this is the proof given in this corollary 27:11. Next we define the prime ideal. This is the definition of prime ideal. Prime ideal is also a proper ideal with the property that AB belongs to n implies either A belongs to n or B belongs to n. Okay, that means if you consider ideal of Z, say 6Z is an ideal. Now you think of two elements. 2 is an element of Z, 3 is an element of Z, but both are not element of 2, 3 are not elements of 6Z. Okay, but when you multiply this 2 into 3, that is 6, obviously a member of 6Z. Okay, that means if you have an ideal, if this is R, then there is an ideal P. Okay, so if you choose an element A from this side and outside P and B from outside B, outside this ideal P, then when you multiply two outside elements, then that will come into that P. Okay, this will not be possible in prime ideals. Okay, that means 6z is not a prime ideal, because outside 6z there are two elements 2 and 3. When we multiply those two elements, then that resultant product is a member of 6z. Okay, so this is not a prime ideal. Prime ideal, the prime ideal is supposed to have this kind of property, that whenever a product is a member of that prime ideal P or N, then one of them, either A is a member of N or B is a member of N. Otherwise, this product will not be a member of N. Okay, so this is the definition of proper ideal, this prime ideal. Okay, a prime ideal, N is said to be a prime ideal if AB is a member of N, then either A should be a member of N or B should be a member of N. Okay, so this is the definition of the prime ideal. Then there are so many prime ideals are there. If you consider 5z, then a product AB belongs to 5z means AB is a multiple of 5. Then obviously one of them is a multiple of 5. Otherwise, the product will not be a multiple of 5. So these are 5z is a 5z, 7z are all example of prime ideals. Okay, so there are so many prime ideals are there, and we have a theorem, theorem 27.15. In this theorem, we say that this R is a commutative unity and N is a proper ideal. Then R by N is a integral domain if and only if N is a prime ideal. Okay, so that is, in order to write the proof of this, we first assume that R over M is an integral domain. Okay, we need to, this is the definition of this is the assumption. Suppose this one, and we need to prove that N is a prime ideal. Okay, we need to prove N is prime. Okay, how will you prove this one? We start a product by assuming that a product is a member of N. Okay, a product is a member of N means the coset containing that product is N itself. Okay, so that means A plus N into B plus N, that is AB plus N, that is equal to 0 plus N. Okay, so this shows that when you multiply two element in R over N, okay, so this is a member of N, then using this member we construct a coset. Since this AB is a member of N, then the coset is same as N. From this you can get two element of R over N. This is a member of R over N, and this is also a member of R over N. When you multiply this, then you will get 0. But our assumption is R over N is an integral domain. R over N is an integral domain means one of them is 0. Either A plus N equal to 0 plus N or B plus N equal to 0 plus N. One of them should be 0 because R over N is an integral domain. There are no 0 devices. So what does it mean? The coset containing A is equal to A plus N, then that is same as 0 plus N. That means A belongs to N. Or the coset containing B is equal to N, that is B is also a member of N. So either A belongs to N or B belongs to N. This shows that this N is an prime ideal. Okay, so this N is a prime ideal because AB belongs to N, then one of them is also a member of N. Then conversely, so you should note this proof for the theorem 27.15, and conversely I will prove the other implication, assuming that suppose N is a prime ideal, you can easily prove that R by N is a integral domain. In order to prove it is an integral domain, we have to prove that it has no 0 divisor. So we multiply two elements to get 0 plus N. We need to show that one of them is 0, okay, which implies AB plus N equal to 0 plus N. Okay, because the product is AB. That implies AB is a member of N. As this N is a prime ideal, one of them is a member of N. Either A belongs to N or B belongs to N. A belongs to N means the coset containing A is same as 0 plus N, or b plus n is equal to 0 plus n, which shows that either a plus n is equal to 0 or b plus n is equal to 0. So whenever a product is 0, then you can get one of them as 0. This proves theorem 27.15. Okay. As a consequence of this, you can easily prove this result. Okay. A maximal ideal in a commutative ring with unity is a prime ideal, because if M is a maximal ideal, then we know that R by M is a field. If R by M is a field, then we can say that R by M is an integral domain, because every field is an integral domain. R by M is an integral domain, then M is a field, M is a prime ideal, because we already proved this one, 27.15. So every maximal ideal is a prime ideal, which proves corollary 27.16. Now we can prove theorem 27.17. In this, if R is a ring with unity, then this map phi of n is equal to n times 1. This is always a homomorphism. This is a trivial thing. In order to prove that phi of n is a homomorphism, we need to start, this is a ring homomorphism. Obviously we need to prove that this is a ring homomorphism. That is, we need to prove two conditions, phi of a plus b and phi of ab. Both we have to evaluate. So first we start with phi of n plus m. By definition, this is n plus 1, n plus m times 1. N plus m times 1 is n times 1 plus m times 1. So this is phi of n, this is phi of m. So that is trivial. And next we have to prove that phi of mn is equal to phi of n into phi of m. Okay, phi of nm is equal to nm times 1. Okay, nm times 1 is n times 1 into m times 1. Then we will get nm times 1. So nm times 1 can be written as n times 1 into m times 1. That is phi of n into phi of m. So this is, we can easily prove this theorem 27.17. That is always a homomorphism. This phi of n is a homomorphism. Now we prove the corollary, that is the consequence of this homomorphism. If we have a ring with unity, characteristic n greater than 1. What does it mean? Since it's a ring with unity, then the characteristic n is nothing but the smallest integer n, such that this 1 is summing up this one n times. Okay, this is 0. So this is the least n. Okay, so this is the characteristic of R. Now if R is a characteristic n which is greater than, not greater than 1, greater than 0, it's not greater than 1, greater than 0. So that is a finite positive quantity. So if this is the case, then what we define this homomorphism Z to R. Okay, so we can say that 1 is mapped to n times 1, right? So this is, what is the definition of this? 1 times 1, and 2 is mapped to 2 times 1, that is in fact 1 plus 1. Actually n is mapped to n times 1, that is equal to 1 plus etc. 1 n times. Therefore this is 0. So actually n is mapped to 0 in fact. Okay. Similarly n plus 1, n plus 2 etc. then 2n. When you observe 2n, that is also mapped to 0. So when you consider R is a ring with the characteristic n, then what is the kernel of this phi? Kernel phi consists of n, 2n, 3n, etc. Similarly minus n. Minus n is also mapped to, what is phi of minus n? That is minus n times 1. This is nothing but this summing up minus 1 n times. Okay, n times. So by taking minus outside, then you can say that this is 1 plus etc. 1 plus n times. That is again 0. So we can say that minus n is also mapped to 0. Obviously 0 is mapped to 0. Minus 2n is mapped to 0. So kernel is nothing but multiples of n. Okay, that is n z. Then using fundamental theorem, we can say that z by kernel z, kernel phi is isomorphic to phi of z. Obviously this phi of z is a subgroup of R. Okay, so kernel is here, kernel is nz, then z by nz is isomorphic to zn. Therefore zn, there is a subgroup phi of z of subring phi of z, subring of this R, which is isomorphic to Zn. So we can say that if R is a characteristic n, then R contains a subgroup which is isomorphic to Zn. Okay, so every ring with a characteristic n contains a subring isomorphic to Zn. Okay, now if we start with a ring with a characteristic 0, okay, characteristic 0 means we can say that if you sum one any number of times, that will not yield 0. Okay, that is the meaning of characteristic equal to 0. So we can say that 1 is mapped to 1, obviously 0 is mapped to 0, and 1 is mapped to 1, and 2 is mapped to 2 times 1, and these all things are never be 0. Okay, only the 0 is mapped to 0. So in that case, kernel phi equal to singleton set 0. That means Z by kernel phi is singleton set 0. This is obviously isomorphic to phi of Z by fundamental theorem, and that is contained in R. Okay, but we know that Z over singleton set 0 is nothing but isomorphic to Z. So we can say that there is an Z contained, Z is isomorphic to this subring and which is contained in R. So we start with a ring with the characteristic 0, then R contains a ring Z. Okay, R containing a subring phi of Z. In fact, that is isomorphic to Z. So every ring with the characteristic R contains a subring which is isomorphic to Z. If we start with a ring with the characteristic n, then that contains a subring which is isomorphic to Zn. This is what we have seen in this corollary 27.18. Actually, that is the computation of the kernel of this homomorphism defined in 27.17. Okay, so if this is the case, then we can easily prove the theorem 27.19. A field F is either of prime characteristic P and contains a subfield isomorphic to Zp, or characteristic 0 and contains a subfield isomorphic to Q. Okay, so if this is the case, if P is the characteristic, then we can say that by previous theorem Zp, previous corollary, Zp is contained in that F. Okay, if F is a field then of characteristic P, then we can say that Zp is there is a subfield which is isomorphic to Zp. So we can say that Zp is contained in F, contained in the sense that there is a substructure of F which is isomorphic to Zp. Okay, and that is the first result. If the characteristic of F is not 0, then above corollary shows that F contains a subring isomorphic to Zp. Okay, so and then we can say that n must be prime. Okay, so because otherwise what happened, if P we can say that if n is the characteristic greater than 0, then we can say that Zn contained in F. Okay, what does it mean? Zn, whenever Zn contained in, or any subring isomorphic Zn contained in F, then we know that this F is a field, so this does not contain 0 divisors. If Zn is contained in F, means Zn should not have 0 divisor. Okay, if Zn has a 0 divisor if and only if has no 0 divisor if and only if n is a prime number. That's why we say that this n must be a prime number. Okay, otherwise this F contains a 0 divisor. Okay, would have 0 divisor in F. Okay. If F is of characteristic 0, we can say that Z is contained in, that is, there is a subring of say what you say a ring, okay, which is contained in F. So this is isomorphic to Z. So we know that Z is a integral domain which is contained in F. So we know that every element of this set will have inverse in F. Okay, not in Z. Z is not a field, but Z is contained in F means there is a subring which is isomorphic to Z, which is contained in F. Therefore, this every non-zero element of this ring should have multiplicative inverse. That means that is isomorphic to Q, because if you complete this Z by adding multiplicative inverses for every non-zero element of Z, that will be Q. Okay, because if we take any Z, any n belongs or any m belongs to Z, then the multiplicative inverse of this m is 1 by m. Okay, so in order to since all these elements of Z are elements of F, then we can say that every 1 by m, every element of the form 1 by m is also a member of F, because F is a field. Therefore every p by q, okay, every element of the form p by q is contained in F. That means F should contain that q. Okay, so this actually this q is called the field of quotient of q, so that is beyond our syllabus, so we need not worry about those things. So you just imagine Z is isomorphic to some ring which is contained in F. Okay, so since F is a field, then every non-zero element of Z has multiplicative inverse in F. That means every element of Q, okay, Q is the set of all Q possesses inverse for every non-zero element of Z. So this Q is always contained in F itself. So we can say that this Q is the prime fields. Okay, there are two interesting prime fields are there. One is ZP, which is always contained in a field with a characteristic P, and Q is contained in a field with a characteristic 0. Therefore these two fields are called prime fields. Actually that's why we define prime fields. ZP and Q are prime fields, because every field, if you take any field, then either the characteristic is P or it is 0. If characteristic P, then that contains a subfield isomorphic to ZP, and otherwise if characteristic 0, then there is a subfield isomorphic to Q. In that sense we can consider these two quantities are prime fields. So with this we can conclude our syllabus. So please give enough time to study all these things. Okay.